right. So today we will first cover the last topics in chapter 7. It's about least square solutions. So here, A is an M times N matrix, so it has n columns, and each column is an m-dimensional vectors. All right, and we consider an inconsistent linear system. Okay, and it is inconsistent because that the B vector is not in the column space of A here. Now, but we try to find a solution. All right, so one of the possible solutions is called least square. So least square solution for such an inconsistent linear system, right? It's a solution, right? So we have to say that to emphasize the solution X such that, right? Because it is impossible to reach the equality, right? So we would like to find an X, right, vector such that the distance between the left-hand side and the right-hand side is minimized. Okay, so such that we want that the distance, right, of the left-hand side from the right-hand side, all right, is minimized. And here the distance is measured in the m-dimensional Euclidean space. Okay. Right. So, so that this is equivalent to saying that if we square the distance, right, we find that this is actually the AX, okay, sorry, is the ith component of this vector A times X minus the ith component of B vector. We take the X value and the square. Yeah, I'm sorry, in my lecture notes I didn't check the X value, so please correct it. We should take the X value because that we may consider complex vectors here. Okay, and look at here. This is actually sum of squares. So this is a sum of squares. Okay? All right, so this sum of squares is minimized. Right? So this explains why this solution is called least square. All right? Because we talk about to minimize a sum of squares like that. All right? Now, if we look at of course, this is a kind of solutions, all right, for this inconsistent linear system, right? And actually, you can set different criteria to find a solution, right, other than to minimize such a sum of squares. Okay, so in general, you can see X is a solution. Okay? It's a solution in some sense. Okay? Of the inconsistent linear system AX equal to B. Right? If and only if we let Y to be the vector A times X, all right? So if only it's that Y is in the column space of A, okay? So basically, you are choosing a Y, right, in the column space of A, all right? So that such a Y will say very close to the B vector, all right? Very close to the B vector, because B is not in the column space of A. Okay? So we are trying to find, and so if we draw a diagram, suppose this is our an m-dimensional Euclidean space. Okay, and we have the column space of A here. All right, but the B is not. So B is here. Oh, maybe this is column space of A, and the B is here. So this is B. So B is not in the column space A. So we try to find a vector Y. Okay, because a solution, if you have a solution X here, then A times X should be a Y in column space. Oh, yep. So maybe I use this color. Okay, so we have so we try to find an Y. Okay, all right, and this Y is actually A times X here. Okay, so we try to find an Y in this column space, right, such that this Y is close to B, right? In the D-square solutions, we measure the closeness by the distance in the m-dimensional Euclidean space. All right. So, okay, and so now we know by theorem 7.1.d, we know that if Y is selected to be the projection of B onto the column space of A. Okay, so if Y is selected to be the orthogonal projection of B onto column space A, then the distance we know is to achieve the minimum for all Y in the column space of A, B minus Y. Right? So this is the 7.1.d. Okay? So this theorem tells us this fact. All right? So the goal is to minimize, right? Is to find an Y. So this is an Y. We want to find an Y such that the distance between Y and the B is minimized, and this Y should be, all right, and the orthogonal projection of B onto the column space of A. Okay, so that to have a solution x which minimize this distance is equivalent to setting. So we should set the ax. So this y is equal to the projection of B onto the column space of A. Okay. Okay, so we have to solve this one. And this is also a new, basically this is a new linear system. And it must be consistent. Okay, because this projection or orthogonal projection is in the column space of A, right? By definition. So this is in the column space of A, all right? So there exists at least one solution. So this is consistent. Okay, so consistent. Right? Okay, so, and of course we can solve it, right? So the first thing to do is to project, to get the orthogonal projection of vector B onto the column space of A, okay, and set this new linear system and solve it. And any solution of this consistent linear solution of this consistent linear system would be this square is the solution of the original inconsistent linear system. Okay, so now we now proceed to prove it, right? To show how to get this x. Okay. Now by definition, all right, of orthogonal projection, okay, we know that Ax is equal to the projection of B onto the column space of A, right? If and only if B minus B minus Ax, right? So if Ax is the orthogonal projection of B onto the column space of A, if only B minus Ax must be in the orthogonal complement of the column space of A. So that means that that we should have orthogonality, right? So the projection. So this one should be the orthogonal projection, and so this vector should be orthogonal to every vector in the column space of A. Okay, so we have this one, and this is if and only if B minus Ax take the inner product with AI because the column space of A, is spanned by the n columns of A. Okay, so that this vector is in the orthogonal complement of column space of A, if only if this vector is orthogonal to every column of A. Okay, and what is this? This one is in general this is AI H and B minus AX. Okay? Of course, if we are dealing with the real case, then the Hermitian, the conjugate transpose is just equal to the transpose. So this is generally true. Okay, so we have that 0 is equal to this one. Okay, and so if we combine them together, okay, so this is equal to 0, 0. Okay, so we combine them together, and this is a matrix which is just the Hermitian of A, means the the conjugate transpose of A. Okay, and B minus AX equal to the 0 vector. So that means that you have A, HA, X equal to AHB B. Okay? All right, so this equation, if and only if to solve this equation, if and only we solve this equation, okay, and it's computable, right? It's computable here. All right, and this one is called the normal equation, okay, for the original problem of solving the inconsistent linear system. Okay, so the original problem of solving the inconsistent linear system to obtain a least squares solution is equivalent to solve this normal equation. Okay, so this is called the normal equation. Right? It's called normal. All right, and so that a solution of the normal equation, okay, which must exist, okay, is called least square. This is square solution of the original problem. Okay, so we have that. Now, in solving the normal equation, the coefficient is actually a linear system, right? And the coefficient matrix, so with the coefficient matrix AHA, right, which is an n times n matrix, right? Called the grand matrix. Okay, called the grand matrix for the set for the ordered set A1, A2, AN of columns of A. Okay. Right. So we call this matrix to be the grand matrix of the ordered set, right? Because we have columns here, and remember the columns may repeat, may not be distinct, right? Because so this is ordered set of columns of A. Right, then the ij entry of G is, you can see Gij is actually AI, H, and Aj. Okay, so it is the conjugate transpose of the ith column multiplied with the jth columns of matrix A. Okay, so Gij is AI, H, and Aj. And so this is actually the inner product, Aj and AI. Okay, so Gij is the inner product of Aj and AI for here. Okay. Right. And so from this observation, in general, okay, we let x v1, v2 up to vn be an ordered set of vectors. Okay, so suppose we have an ordered set of vectors in an inner product space. Wait. Okay, so these vectors may not be column vectors in the Euclidean space, just vectors in arbitrary inner product space V. Okay, so they have so just arbitrary. So and the grand matrix Gij, the grand matrix for S, for this ordered set of vectors in a general inner product space. Okay, very general. Okay, right? It's defined as, right. So the Gij is defined to be the Vj and the Vi. Okay, for Ij from 1 to n. Okay, so we use inner product to define the entries of the grand matrix for this ordered set. Okay, so we have ordered. So it's quite general. So for this ordered set, maybe some of the n vectors are the same. Okay. Okay. Right. So we have an ordered set there. And so if you like, you can expand the G Okay, you can look at this is V1, V1, and V2, V1, and the Vn, V1, and here it's V1, V2, and the V2, V2, and Vn, V2, all right, and V1, Vn, V2, Vn, and Vn, Vn. Okay, so the grand matrix is formed by taking the inner product of two matrices in the ordered set. Okay, so this is quite general, right? Quite general, right? And the grand matrix here for the normal equation, just a special case that this is the grand matrix for the ordered set of columns of matrix A. Right? Okay. So sometimes when you deal with in C, the inner product space of all continuous function defined on a finite interval from A to B. This is a function space, right? And in this function space, if you have n functions here, then you can form a grand matrix for such an ordered set of functions. Okay, and this grand matrix will give you the information about that the inner product between vectors in this ordered set. Okay, so this gives the information of inner product. All right, so now the theorem. So now we write down a theorem. So so now the ordered set X, V1, V2 up to Vn of vectors in an inner product space right? In the product space, right? So the ordered set is linearly independent if and only if the grand matrix G for X is an n times n invertible matrix. Okay, and this is a very useful theorem because sometimes we want to check whether an ordered set of vectors in a general inner product space to be linearly independent. I want to check. Then, because they are, for example, they are functions, right? So how to check they linearly independent? If you recall that the checking of linear independence about arbitrary set in a general vector space, all right, and it depends on the knowledge, right, of the vector space, right? Especially if you deal with function vector space. Okay, but the theorem gives you a very good idea. It's very simple because you can construct a grand matrix, and the grand matrix is numerical. Why? Because grand matrix give you real numbers or complex numbers. So they are matrices, okay, of scalars. So they are numerical, and you can check whether this numerical matrix to be invertible or not. Much more easier. Okay, so it is a very good tool for us to check whether a set of vectors in a general inner product space to be linearly independent or not. All right, so that's quite useful. All right, and a proof is here. All right, so we prove the reverse direction first. Okay, so here, to prove the reverse direction, everybody says that if the grand matrix G is an invertible matrix, then this set is linearly independent. So suppose, so we use contradiction, right? So suppose X is linearly dependent, right? So, and we want to prove that we get to a contradiction. All right, so they are, there is a non-trivial linear relation, all right, on S, all right? So we have a non-trivial, all right? So such that alpha 1 V1 plus alpha 2 V2 plus plus alpha n Vn equal to the 0 vector. Okay, and with the scalars alpha 1, alpha 2 up to alpha n, not all zeros. Okay, so some of the coefficients, all right, at least one of the coefficients is non-zero. Okay, so such a linear relation is called a non-trivial linear relation. All right, so now then for all I from 1 to n, okay, so now we know that we have a 0 vector Vi is 0, right? So if we take the inner product of Vi with the 0 vector, it's 0. But we know this is the summation. All right? 0 is, we plug into this non-trivial linear relation. So we have alpha j and Vj and the Vi here. Okay, and what is that? Alpha j, and this is G I j. Okay, so this is true. This is true for all the I from 1 to n. Or I from 1 to n here. Okay, and so now you can see that. If we put them together, so this is saying that. So this is equal to the summation j from 1 to n alpha j and the Gij, and so this is G1 j, right? And summation j from 1 to n alpha j, G2 j, etc. up to summation j from 1 to n alpha j and G and j. Okay, so you see here, and so this is j from 1 to n alpha j, and this is G1 j, G2 j up to G and j. And this is 0. So that means that, and this is the jth column of the grand matrix, right? So this is the jth column of the grand matrix, and so that the n columns, so the n columns of G, right, form a linearly dependent set. Right, because this is a linear relation, and the coefficient alpha j, at least one of the alpha j is non-zero, because here non-zero. So that this the n column, and this is saying that G is not invertible. Okay, by the inverse matrix theorem, Okay, so, and this is a contradiction. Because that G is assumed to be invertible. Okay? So we get a contradiction. So X must be linearly independent. Okay? So this is our conclusion. Now the forward direction here. All right, so we consider an arbitrary. So now S is the linearly independent set, right? The forward direction means that if X is linearly independent, we want to prove G, the grand matrix, is invertible, right? So to show that grand matrix G is invertible, we have to show that the n columns of G is linearly independent. Okay, so we consider an arbitrary linear relation on the n columns of G. Okay, so actually we have saying that so we do the, so this is 0. So we consider this is the, and the G, 1J, G2J, G and J. Okay, so this is the with scalars alpha 1, alpha 2 up to alpha n, not alpha. Okay. Okay, so we consider the arbitrary linear relation. So this is a linear relation, right? On the n columns of G. This is a linear relation. And we want to show that such a linear relation implies all the alpha j should be 0. This is what we want to prove. Okay? This is what we want to prove. Okay, and so that we manipulate, we move into that. Okay, so this vector is 0 vector. So this is only if that j from 1 alpha j and the g I j is 0 for all I from 1 to n. Okay? But why is that? Alpha j And by definition, the entry, the Gij entries is Vj, the inner product of Vj and the Vi. Okay? Okay? And this is 0 for O1 to I if En. Okay? This one. And so that we absorb into it, so alpha j, Vj, and Vi is 0 for all. And here, is that okay? All right, and so now we combine them, so we form the same alpha I. Okay? So this inner product multiply with alpha I, okay? And take the bar here. And the sum together, okay? Also 0, right? Okay? And we move to the second argument. So we have alpha j, Vj, and here is I from 1 to n, alpha I, Vi, and this is 0. But these two vectors are the same. Okay? The same vector. So by the non-negativity of inner product, right? So this is saying that summation alpha j, Vj is the 0 vector. This is only choice. Now, we have a linear relation on Vi's. We have linear relation on Vi's, but we assume that S is linearly independent. So this saying that, this implies that alpha j is 0 for all j. Is 0. Okay? So we start with an arbitrary linear relation, and we find alpha j must be all zeros. Okay, so that the n columns of G form a linearly independent set. Right? So the n columns of G form a linearly independent set, and so this is if only if that G is invertible by the inverse matrix theorem. And we have done. So we prove the theorem. This is the forward direction. Okay, so we now complete the proof of that. Okay, so now we can apply the theorem now to solve our normal equation here. Okay, so now if the m times n coefficient matrix A, okay, of an inconsistent linear system Ax equal to B. All right, so suppose the coefficient matrix has a rank A equal to n. Okay, so suppose that, and The rank of A is n, and is also called, this is also the column rank of A, right? Okay, so this is actually the rank of the column space of A. Same. So it means that the n, so i.e. the n columns of A is form a linearly independent set. Right? So suppose, so if we have this situation that the matrix A, okay, is n columns, and these n columns form a linearly independent set, then the grand matrix G, it's AHA, is invertible. Okay? So by our previous theorem, 7.2.4, right? So the grand matrix is invertible, and there is only one least squares solution, right? And this is square LS solution. We call LS. It's AHA inverse AHB. Okay? Since the normal equation AX equal to AHB has a unique solution. Okay, so you know that so if the rank of A is equal to n, the number of columns of A, then we have a unique this square as a solution. Okay, here. Of course, if this is not the case, if the rank of A is less than n, then you will have infinite many solutions, of course. Okay, so it's not unique. All right, so now we finish chapter 7, and now we are going to chapter 8, the last chapter of this semester. Okay, and the first 7 chapters give us the foundation of linear algebras. So all basic concept has been developed up to now, and in this chapter we want to develop further results. Okay. So the first section is about the spectral theorem. Okay. Oh, and we were in here again. We will use F to denote R or C here. Okay. All right, and to discuss the spectral theorem, we will divide the discussion into three subsections. So the first one is to introduce the concept of linear functionals. Okay. All right. So let V a vector space. Right. So we go back to study general vector space. So V is a vector space over F. So over R or over C. Now, and then F, then a linear transformation. Okay, F from V to F. Okay, it's called a linear functional. On V. Okay, so linear functionals on V is just a special kind of linear transformation. All right, it is a linear transformation from the vector space V to the scale field, and we know F is a one-dimensional vector space over F. Okay, so this is one-dimensional. Okay, and now let's see some special types of linear functionals. Indeed, we should be familiar with linear functional because we use that a lot. Okay, so let's see. All right, so suppose we are given n scalars, say A1, A2 up to An. So we are given n scalars, and we define a function f from the n-dimensional Euclidean space to the scale field, the set of all scalars here. Right, and the definition is that we by doing the things that, okay, for each vector in the n-dimensional Euclidean space, we map to a linear combination or a sum weighted by the chosen scalars. So this AI, Xi. Okay. Okay. So that is the case here. Right. Now, for all x and y, right? We want to show this function is linear. Okay. In Fn and the alpha, beta in F. Okay, so we know that the linear combination alpha x plus beta y, okay, has component alpha x1 beta y1, alpha x2 plus beta y2, etc. Alpha xn plus beta yn here. So that the value of x at this linear combination, by definition, which is equal to, this is sum, weighted by ai, alpha xi plus beta yi here. And so we can do some algebraic manipulation. So this is xi. Okay, so this is alpha fx plus beta f of y. Okay, right. So which shows that f is linear, and then a linear function on Fn. Okay, so this is about show us how to construct linear functions on Euclidean space. Okay, it's easy, right? Because you can choose arbitrary n scalars, not necessarily distinct, just n scalars there, and to form this weighted sum here. Okay. All right. Now we let V star to be the set of all linear functions on V. Okay, so we call it V star. Okay, and an immediate theorem is to say that V star is a vector space over F. Okay, for any vector space V over F. Okay. Okay. So given an arbitrary vector space V over F, then we can construct V star, right? The set of all linear functions on V, and then we will show that V star is a vector space. Right, and the proof is here. Right, so we let F G is in V star, and A, B is in R scalars. Okay. Now we look at their linear combination. Okay, we look at their linear combination. We will show that this linear combination is also a linear function. All right, so we look at alpha x plus beta y. Okay, so we operate it, and this is equal to alpha f of x plus beta y. AB, sorry, it's not alpha. A and the B of G alpha X plus beta Y. Okay, by definition. Okay, and this is A, and the alpha f of X plus beta f of Y plus B alpha G of X plus beta G of Y. All right, and we regroup the things. This is A of fx plus B of gx, okay, plus beta of A of fy plus B of gy together. All right, and then by definition, this is AF plus BG of x plus beta, and this is AF plus BG of y. Okay, and so you can see that, consider this as a function, right? So this function has linearity. This implies that AF plus BG is also in V star. Okay, so every linear combination is also a V star. Okay, and of course you can check. So that V star is closed under vector addition and scalar multiplication. Okay, and we can check those 7 axioms are valid, okay, for V star. Okay, so V star is a vector space. Right. Of course, we have to check one by one, but they are functions. Okay, but they are linear transformations, so that there are special types of linear transformations. So that should be the case. Okay, so V star is a vector space. So we will give a name for V star. And as we can see, whenever we have a vector space V, then we will have a V star, okay, automatically, right? And so V star is called the dual space of V, okay? So this is called the dual space of V. Now the next question is that if the V is finite dimensional, say if the V has dimension n, can we determine the dimension of V star? Okay. All right. So this is the next purpose is to determine the dimension of V star. Once we know the dimension of V. Okay. So we let B suppose that right, so that B is a basis. Okay, sorry, maybe I say, okay, first V an n-dimensional. So we consider n-dimensional vector space. Right. And B, U1, U2 up to UN, a basis for V. All right. And by theorem 2.4.12, a linear function so a linear function f on V will be uniquely determined by its value at basis vectors UI. Okay? This is a general. So in this sense, we say any linear transformation can be determined by its value at the basis vectors. Okay? So in particular, right? So in particular, for each j from 1 to n, we define a linear function called fj from V to F by, so the fj function, okay, so now we will specify its value at the basis vectors. Now, so for fj on ui, the value at vi is 1 if I equal to j, but it's 0 if I is not equal to j. Okay. So this specification uniquely determined fj. All right? This uniquely determined fj there. So we have that. Okay. So now for all x in the vector space, the x can be written as a unique linear combination of the basis vectors in this basis B. Okay, so this is the unique representation. Okay, and here the coordinate is just x1. Okay, so we know that this is the coordinate vector, right, relative to the basis B. Now, so fjx, so let's look at. So the linear function at x, okay, so this is fj summation I from, so this is xi fj and ui. Okay, but by our specification, that if I is not equal to j, this is 0. All right, so only when I equal to j, this is 1, and we have xj. So what is that? Fj operate on x, give the j's component or the j's coordinate, right? Relative to the basis, this coordinate system B, right? Because a basis form a coordinate system. Okay, so this indicates that this shows that Fj is just the j's coordinate function associated with the basis B for V. Okay, so you see that when we define Fj here, this Fj is relative to a selected basis here. Okay, so once we fix a basis, we fix a coordinate system, and then the Fj on x give us the j's coordinate, all right, in the B coordinate system here. Okay, so the functional, just this functional here, just coordinates functions we have. Now we are able to prove the following theorem. V is an n-dimensional vector space. B, U1, U2, Un is a basis for V. Okay? And the B star is F1, F2, up to Fn. Okay? All right. Then, okay, then the set, all right? So the set consists of coordinate function of coordinate functions, all right? Coordinate functions associated with B, right? So B star is the set of coordinate functions associated with the basis, this set. Now it's a basis for the dual space V star. Okay, so actually we find a basis for V star. Once we have a basis for V here, then then the set of all coordinate functions associated with B becomes to a basis for the dual space V star. So in particular, if the dimension of V star is equal to n, is equal to the dimension of V. Okay, so if V is an n-dimensional vector space, then its dual space V star has the same dimension n. Okay, and also we find out a basis. Okay, and this basis corresponding to a basis for the vector space V. Okay, and for this reason, the B star is called the dual basis. So this one called the dual basis of B. Okay, so B star is called the dual basis B. All right, so we have to show the proof that this is a basis. To show this is a basis, we have to check two things. First of all, we have to check that the dual space V star is spanned by B star. And the second, we have to show that B star is linearly independent. Okay. All right. So let F is in the dual space means that F is a linear function. So now for all x in the vector space V, we know x can be written as a unique linear combination of the basis vectors in B. Okay, so we have that. Then we have that the function value of f at x okay, and the bilinearity okay, bilinearity here. Okay, and this is I from 1 to n, but xi is the coordinator, the ith coordinator of the vector x in the B coordinate system, right? And we know xi is actually fix and fui. Okay. Okay. So xi becomes to fix here. And so now fui is a scalar. So now we write this as a scalar, okay? Scalar and fi here and x. And so this is becomes to fui times fi and x. Okay? Alright, so this implies that f is actually a linear combination. Fui times fi. Okay, it's a linear combination of the coordinate function. So this is implies that f is in the span of the B star. Okay, B star here. So every vector in B star is in the span of B star. So we have B star is contained in the span of B star, and so this implies that because the span of B star is the subset of V star, so we have that the V star is equal to the span of B star. Okay, so this is the first step. Okay, so this is the first step that we know that B star is a spanning set of V star. Next, we have to show that B star is a linearly independent set. All right, so we consider a linear relation on the B star. Okay, so alpha 1 F1 plus alpha 2 F2 plus da 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 plus alpha n Fn equal to the 0. This 0 is the 0 linear functional on V. Okay? Right? So with scalars alpha 1, alpha 2, up to alpha n. Here. Alright, so now, so this is true, right? It's zero functional. So that for all I from 1 to n, we know 0 is the zero functional has zero value at every vector, right? In particular ui, and this is equal to ui, and this is equal to I use j here, sorry, use j. Okay. Now, but as we know, okay, because this is coordinate function, so that if I is not equal to j, this is 0. And so it is 1 if and only if I equal to j. So this is equal to alpha I. So alpha I is 0, right? Alpha I is 0. So prove that alpha I is 0. Okay, so that V star is linearly independent. Okay? Because every linear relation gives us trivial relation, right? Because all the coefficients must be 0. So B star is linearly independent. Okay? So with conclusion is that B star is a basis for V star. Okay? So this is the end of proof. Okay? So now let's see what we get up to now. Okay, and so we have dual space. Okay, for every vector space, we have a dual space V star. Okay, and if the V is n-dimensional and we have a basis for V, then we can construct a basis, dual basis B star for the V star. Okay, B star for V star, and so that V star has the same dimension as V. Okay, so all of this is on general vector space. Now, if we get into, if our vector space has an inner product, okay, so what extra information do we get? Okay, so maybe we take a 5 minutes break. Okay. Okay. And now, so now we can see the V is an inner product space over F. Okay. Now, for each vector in V, we define a function called FV from V to F by X goes to the inner product of X and V. Right? So for every X, you take the inner product of X with just fix the V. Okay? I.e., the FVX is defined to be okay, and because the inner product here, so we have linearity for the first argument, right? So by the linearity, of inner product for the first argument, every FV is a linear function on V. Okay, so to construct linear function on an inner product space is very easy. Okay, just you can select any vector from the V, okay, and define a function. Just take the inner product with V. Then such a function becomes to a linear function. All right, and so it's very interesting that this is a very simple way to construct, right? And so that so we have the following theorem, 8.1.c. So V is inner product space. Over F, okay, and the T is from V to V star, and the association is that for every vector in the inner product space, we go to the linear function of F sub V. Okay, so actually this construction established, all right. Right, it's a mapping, and this mapping, right, the mapping, okay, is linear if F is equal to R, and the conjugate linear if our scalar is complex. Okay, so this association for every vector v in the inner product space capital V, we have a linear function of f sub v. Okay. So this association gives us linear transformation if in the real case, but for the complex case we have conjugate linear transformation. I will define later. Furthermore, T is injective, right? So T is injective. Okay, so different V give us different linear function, and the T is suggestive. All right, so this is very important. So T is onto means that every linear function can be constructed by this way. So T is suggestive if when the V is finite dimensional. Okay, so when the inner product space V is finite dimensional, then T is suggestive. All right, so look at the T alpha V plus beta U. Okay, so now we take for V U in the inner product space V, and the alpha beta are scalars. Now we look at the image of this mapping T at the linear combination of V and U here. And this is actually, we know, all right, and so operate on all the vector x, and we know this is f of alpha V plus beta U on x. So consider for all x in V, we have this one. Okay, and so this is x alpha V plus beta U here, by definition. And this is alpha bar xv plus beta bar xu. Okay, and so this is alpha bar fvx plus beta bar fux. And this is fvx is t vx. Or, oh, okay, maybe I fv plus beta bar fu x. Okay. So now this is alpha bar tv plus beta bar tu. Okay. All right. So from here, we know that t alpha v plus beta u is equal to alpha bar t v plus beta bar u. So this is conjugate linear because that the coefficient conjugate linear. Okay. But when f equal to r, then alpha bar equal to alpha, beta bar equal to beta. So that t alpha u plus beta v. Oh, sorry. T alpha v beta u equal to alpha tu plus beta tu. Alright? This implies t is linear. Okay. Okay, so the first part has been proved. That all right. So the mapping is linear for the real case, and is conjugate linear for the complex case. Okay, so to show T is injective, now we look at, so if Tu equal to Tv equal to Tu, right? So suppose that T has the same value at the two vectors U and V and U, i.e. Fv equal to Fu. Right? Then, okay. Then we have, when we apply these functions, okay, it will be the same. But this is the xv. And this is the xu. So this implies that xv minus u is 0 for all x in v. Okay? So when you move to the left-hand side, you get this one. All right. So by letting x equal to the difference vector, we have equal to 0, and this implies that okay, thus T is injective. Okay, so now T is injective. So now we assume V is n-dimensional. Okay? So we assume V is n-dimensional, and we let B, U1, U2 up to UN be a basis for the inner product space V. Okay? Probably I use V. Maybe better. V1, V2, Vn. Okay, and so consider a linear relation on the set f v1, f v2 up to f vn. Okay, so from this basis we can construct a set of linear functions, right? F V1 V2 Vn. Okay, so such a alpha 1 FV1 plus alpha 2 FV2 plus plus alpha n FVn equal to 0. Okay, and this 0 is the zero linear function, no? On V. Okay, so we have with the scalars alpha 1 up to alpha n. Okay, all right, so now for all j from 1 to n, all right, so we have as before. So you can conjecture that this conjecture, let's say it's a linearly independent set. Oh, by the way, I'm sorry. Sorry, not just the basis, Bn also normal basis. I'm sorry, or V. Okay. Okay. So we take the orthonormal basis. Okay. Okay. So we can, because V has an inner product structure. So we can have a stronger basis, which is orthonormal basis. Okay. Right, and for this orthonormal basis, so actually the corresponding set of linear function, you can see that it is also linearly independent in here. That so we apply on the V, so 0 is the 0 Vj, okay, because it's zero function. And this is the summation from I from 1 to n, alpha I f Vi, okay, on Vj here, okay. Because that this is a linear relation, so that this linear combination is the zero linear function. Okay. Okay, and so alpha I f Vi Vj here, but this is by the definition. This is actually equal to Vj and the Vi here, the inner product. But we know Vi's are also normal to each other because we purposely select an orthonormal basis. So that this inner product is 0 except I equal to j. And when I equal to j, this inner product is equal to 1. And so this is actually equal to alpha j. So we know alpha j is 0. Okay, immediately. Okay, so alpha j is 0. All right, so that fv1, fv2 up to fvn is a linearly independent set of n vectors in the dual space. Okay, but the dimension of the dual space is n. So this one implies that fv1, fv2 up to fvn is a basis for V star by theorem 5.2.10. Okay? 5.2.10 says that if we have a linear independent set of size n is equal to the dimension of the vector space, then this linear independent set is a basis. Okay, so this is a basis. Okay, got that? So now for each, so we have basis, right? So now for each V in the V star, there exists unique alpha 1, alpha 2 up to alpha n, okay, such that F is the linear combination of FVI's okay, so we know because this is a basis already, right? So you can see that this is actually, you can regard this as a dual basis. So for inner product space, you choose an orthonormal basis for V, then this is called the dual basis of V. Okay, this is called the dual basis of V. Right. And you can see this is actually coordinator. This is indeed the coordinator of a function of this basis. You can check that. Because of 0, 1, this is relationship. Okay? Because here you can see FVI, Vj is delta Ij. Okay, so you can see that this is indeed the dual basis we defined before. Okay, so these two concepts the same, right? So this is the dual basis. Okay. From here, because this one is equal to this one, and this is the delta Ij. Okay, it's equal to delta Ij. And delta Ij is 1 if I equal to j, 0 if I not equal to j. Okay, so this is actually the dual basis we defined before, the coordinate function. Okay, so they are the FVI is the ice coordinator function, right? Associated with this orthonormal basis. Okay, so this construction give us by using the inner product give us the coordinate function. Okay, so this is the coordinate function. Okay. Anyway, so that this is the dual basis, coincide with what we defined before. Okay, so they are coordinate functions there. And now we back to our proof here that we already show this B star, right? So the dual basis, this set is a basis for V star already. So that every linear function in V star can be written as here, right? Can be written as the unique linear combination of FVI's. All right, so now for all x in V, we look at the value. So this is summation x, right? So this is, we look at alpha I, fvi, and x. And by definition, this is the inner product of x with vi. Okay? And you can observe of this summation I from 1 to n by using the complex conjugate of our I and the vi. Aha, and you see, what is this? This f actually can be constructed by f of summation of I bar and vi here of x. So that this proves that f is equal to f. So we can find a vector okay. So every linear function is indeed an fv for some v. Okay, so T is suggestive. End of the proof. Okay, so this is very important. Okay, that we have T suggest if the inner product V is a finite dimensional, then its dual basis V star. Every linear function is indeed f sub V for some V. Okay, so the mapping here, this mapping becomes to suggestive untrue. Okay, so if V is a finite dimension inner product space, then the mapping T is 1-to-1 and untrue. So it's a bijective mapping. In the real case, it is a linear isomorphism. In the complex case, it's so-called conjugate linear isomorphism. Okay, right. Okay, and so now we are able to move on to the next topic to talk about the adjoint of a linear operator. The adjoint of a linear operator. Okay, so in this subsection we will let V to be a finite dimensional inner product space. Over F. Okay, so V is a finite dimension. It's very important. Okay, very finite dimensional. So a lot of good things happened. For example, V star, its dual base has the same dimension as the dimension of V. Second is that V star, every linear function is actually obtained by taking the inner product with certain vector V in the inner product space, capital V. Okay. All right, and so consider T as a linear operator. Right, on V. Okay, and so now for each y in V, okay, we define theta y, right? We to be the conjugate, right, of t, the linear operator, with a linear functional defined by y. Okay, so the situation is here. We have v to v, this is go to t, and we have f, this is go to y. Okay, and so now the theta y is just the composite of t and fy here. Okay, so of course, because of the t, the theta y in general is a different linear function from linear function of fy, right? So theta y and the fy are two different linear functions. In general, you can see here. Now, okay, so this is composition. Linear transformation, composition of two linear transformation is also linear transformation. This is by theorem 5.2.b in chapter 5. We know theta y is a linear functional. Again, a linear functional. So this is a linear functional on v. Now we just prove theorem 8.1.c. So by theorem 8.1.c, okay, so there exists a unique z vector in V such that theta y is actually equal to, so that theta y is actually equal to fz. Okay? So indeed, theta y, because it's a linear function, so by theorem 8.1.c, because the mapping is surjective, okay? So this linear function is fz here. So such that theta y x equal to, so this is the inner product for all x in V here. Okay? Right? And also theta y, it's fy. Remember? So the theta y is constructed by this composition. And so this is equal to, so this is y for all x in V. Okay? So now we obtain an interesting result. So we have t of x, y is equal to x of z for all x in V. Okay? And here, z is uniquely determined by y. Okay? From the previous slide, you know that z is uniquely determined by y. Okay, so we let we let Z to be so-called T dagger Y. Okay? Right, so we have some, so in this mechanism, all right, we know this is equal to Fz. So from Y, you get the Z here. Okay, so Z depends on Y. It depends on Y here. And so we denote Z as a function of Y. Somehow, there's a mechanism. Okay, and so thus, we establish a mapping. So we establish a mapping T dagger, okay, from V to V, okay, such that we have a functional relation Tx Y is equal to X T dagger Y for all X in V. Okay, so we establish this mapping here. So whenever you have X and Y arbitrary vector in the finite dimensional inner product space V, then this inner product is equal to another inner product. But here we have X here, but the Y has been replaced by T dagger Y, means the Z here. Now, so T dagger is called the adjoint of T, because each T has a T dagger. Okay, so it's just like a you can't say it's twin, but means that if a people has a front, then it will have a back. Okay? So linear transformation is just like in front, and the T dagger just in the back, right? So they are always associate it together each other. This is just like if you have a V, you have a dual space V star. Now, if you have a linear operator on a finite dimensional inner product space, then you have another mapping here called T dagger adjoint. Okay, from V to V. Okay. And of course, we have to show that this T dagger is also a linear operator on V. Okay, so we will show that immediately. Okay, but you have to look at the construction of the joint. Indeed, we just described the mechanism, how we establish this mapping T dagger, right? So that this mechanism is successful because that we have theorem 8.1.c, right? Because every linear functional has the form f of v, f sub v. Okay, so that so we have this functional this is very important functional relation between a linear operator and its adjoint T dagger. Okay, here. All right. Theorem 8.1.d says that the adjoint T dagger of a linear operator T on a finite dimensional inner product space V is a linear operator on V. Okay, so we want to show that T dagger is a linear operator on V. All right, so we consider T dagger alpha 1 y1 plus alpha 2 y2 for y1 y2 in B and alpha 1 L2 in F. Okay, right. So we consider the image of the T dagger of this mapping at this linear combination. Okay, this linear combination. All right. So now for all x in V. Now, okay, x T dagger. So we take the inner product. All right, so we take this image. This image is a vector in V. Okay, right. Take this inner product. So by the functional relationship here, this is equal to Tx, and here we have alpha 1 y1 plus alpha 2 y2 here. Okay, and for the second argument, inner product has conjugate linearity. So we have alpha 1 bar Tx y1 plus alpha 2 bar Tx and y2 here. We have that. Okay, so this is, and again, by the functional relationship, this inner product is equal to x with T dagger y1. X T dagger y2. Okay, and so again, we absorb the coefficient to the second argument. So we have alpha 1 T dagger y1 plus alpha 2 T dagger y2. Okay. So this inner product is true for all x in V. So this implies that so T dagger alpha 1 y1 plus alpha 2 y2 is equal to alpha 1 T dagger y1 plus alpha 2 T dagger y2. Okay, so T star is linear. And we have done. Okay, so we have shown that the adjoint T dagger of a linear operator T is also a linear operator. Okay? Okay, and so now we talk about a lot of things on linear operators. Let's take an example. Okay, so example that consider a linear operator from Fn, go to Fn with Tx is equal to Ax for all x in Fn, where A is n times n matrix over F. Okay? So this is a general linear transformation linear operator on Euclidean space, right? Because as we proved in chapter 3, every linear operator on the Euclidean space is this form. We can find a matrix A here. Okay, so so now our question is, what is T star? Okay, so what is this adjoint? And we know the adjoint T integer is also a linear operator on the Euclidean space. So there is a matrix, right, associated with T integer. So what is this matrix? What is this matrix? Okay, so that is the question. All right, so to resolve this question, now always think about the functional relationship. So for x, y in the Euclidean space, we have here t, x, y here. And by definition, this is ax and y here. Okay? This is ax, y. And this is y, Hermitian, and ax here. Okay? Right? Because at the definition, we have destination we need here. Okay, so starting from there, we have to go to, this is our destination. Okay, it's our destination. So now, we have to let diff x here. So we have to associate x to the second argument. So we find this is y, x here. This is the way we have. Okay, and so this is, what is that? So this is x and y. Okay, and this is exactly equal to x t dagger of y. Okay, so we established so this says that t dagger y is equal to ahy for all y in Fn. Okay? All right, and when f is equal to r, then t dagger y is just A transpose of y for all. Okay. Okay, so we answer the question that the t dagger is actually, so if A also, matrix A associated with the linear operator T, then the matrix associated with T dagger is just the Hermitian of A, the conjugate transpose of A in the complex case. In the real case, just the transpose of A only. Okay. So this is the reason. Okay, so this is the reason why the conjugate transpose AH or the transpose AT of A is sometimes called the adjoint of A. Okay, when F is equal to C, or when F equal to R. Okay. When F equal to R, then the transpose of A is called the adjoint. So do not confuse with the classical adjoint we discussed in chapter 4 when we discussed the determinant. There we discussed the so-called classical adjoint. Okay, because the classical adjoint corresponding to the covectors, right, of a matrix. Okay. But here we are talking about the conjugate transpose of A for the complex matrix A, or the transpose of A for real matrix A. Okay. Okay, so the joint actually is not a stranger for us, right? Especially for linear operators on Euclidean space. So this is the many times, many situations we encounter a linear operator on Euclidean space. And so for any linear operator on the Euclidean space, it's adjoint actually correlated to the conjugate transpose of the matrix, the orientation. Okay. Okay. But okay. But a general theory for adjoint has to be developed in the previous discussion. Okay, through linear functional. Okay, and to establish theorem 8.1.c. Okay, to show that how can we construct the linear functional. Okay. Okay, all right, so and this example can be extended as a generalization. So let's look at all right, so suppose B, U1, U2, UN, okay. Oh, sorry. So V is an n-dimensional inner product space over F, and B, U1, U2, up to UN, and also normal basis for V. Now, for any vector xy in V, we know that the coordinate, so we can so every x can be written as a linear combination of the basis vectors in this also normal basis. And the coefficient, the coordinate actually is quite easy, just the inner product of x with ui. Okay? So we have all right. So this is saying that the coordinate vectors just right. So this is the the b coordinate of x, and the b coordinate of y is just okay. So they are coordinate vectors we have. And so that when we want to take the inner product of x and y in V, so we can just write down, right? Summation I from 1 to n, and x ui, and here is j from 1 to n, y uj, okay? And then you expand. So, okay, and this scalar comes out here, but when the scalar in the second argument comes out, you have to take the complex conjugate, right? And you have ui, uj. Okay. But because ui, uj, they are also normal to each other, so that this has become to just a single sum, right? So we have x and ui bar y uj here. Okay? So the sum here. But what is that? This is actually by using the coordinate vector, the emission of okay, this one, or you can use the dot product. Dot. Fine, right? So very interesting, right? The inner product, when you want to perform the inner product of x and y in V, in the inner product space V, you can obtain the same result by taking the inner product of the corresponding coordinate vectors in the Euclidean space. Okay, in the Euclidean space here. So you can use the coordinate vector to show that. So that is convenient. But of course, you have to find the coordinate vectors first, right? Right, before you can do the computation. So, okay. Now we let T a linear operator on V, and the T dagger, the adjoint of T here. Okay. Now again, in here, so with that, we have, by using the B coordinate system, we know we have that. Okay, so we have this one. And for here, the K coordinate system, dagger, T dagger. Okay, so we have these two. All right, so this is the metric representation of the linear operator T relative to the basis, the orthonormal basis B. And this one is the metric representation of the T dagger relative to the same orthonormal basis. And we want to know the relationship between these two matrix representation, okay? Between these two matrix representation. All right. So okay. All right. Now, so things we have the functional relationship. Okay, we have this functional relationship. So these two inner products are the same. Okay. Okay. But this one is by our previous discussion, this is we can compute the inner product by using the coordinate vector. Okay. And by using this one, so this is y, and the t, and the x. Yeah. The other way is x, t dagger y. So this is t dagger y, emission, and x b. Right? But this one is t dagger b, and the y b, you take the Hermitian, and the x. Okay? So finally you have y and t dagger bh and the x. Right? Now, because now they are equal, so this is implies that t is equal to t dagger bh. All right, so this is implies that t dagger b is equal to the Hermitian of the metric representation of t. Okay, so this proves the following generalization of the previous example. Okay, and we call it a theorem 8.1.e. That t dagger b is equal to where b is an orthonormal. So it's very important, B is an orthonormal basis for V. Okay. Right, so we have this relationship. Okay. Right. Now, a linear operator. So all right, so okay, a linear operator T on V is called self-adjoint if T dagger is equal to T itself. So self-adjoint means that T dagger is equal to T. So i.e. it means that Tx y equal to x ty for all x in V. Okay. So this is the functional definition of a self-adjoint linear operator. Okay, so a linear operator is called self-adjoint, and the self-adjoint linear operator is important and has many useful properties, including the following properties. So suppose that V again it's a finite dimensional inner product space over F. Okay. And T is a self-adjoint linear operator on V. Okay. Then we have two properties. First, every eigenvalue of T, of course, if it exists, okay, it's real. Second, if U and V, are eigenvectors of T corresponding to distinct eigenvalues lambda and mu respectively, then so if we have two eigenvectors corresponding to distinct eigenvalues, then these two eigenvectors must be orthogonal to each other. Okay. So these two properties are for self-adjoint linear operators. Okay? Proof. First one. Okay, so by definition, every eigenvalue of T, if it exists, is real when F is equal to R. Okay, because if the scalars are real numbers, of course we find eigenvalues which are reals only. Okay, so if this must be real, so we assume the complex case. Okay, all right. So we let lambda be an eigenvalue of T with a corresponding eigenvector V. Okay? Then, all right, then we look at the right. Then we look at this inner product, TV and V, and we know this is lambda V and V. Also, look at V and TV. So we have V and the lambda V here. And here, by linearity for the first argument, and by the conjugate linearity for the second argument, we have that. And because T is self-adjoint, so these two are identical. So they are equal. So they are equal. So this implies that lambda equal to lambda bar. And this is implied lambda equal to lambda bar. Implied lambda is real. Okay, so we have done. Okay, so for the complex case, if an eigenvalue exists, then this eigenvalue must be real. All right, now suppose we have two eigenvectors, all right? And so now we consider Tu and the V. Okay, so we consider, all right, and so they are the same as UTV. Okay, they are the same because P is self-adjoint. And this one is lambda U V. And this one is mu V. Okay, because U is an eigenvector corresponding to eigenvalue lambda. V is an eigenvector corresponding to the eigenvalue mu here. So we have that. Okay, and this is and this is lambda U V. Okay, and this is the mu U V. But from 1, every eigenvalue should be real. So this is mu U V. Okay, by 1 in above. Every eigenvalue is real. So this one. And so they are equal. So they must be equal, right? So this is saying that lambda U V equal to mu U V. And this implies lambda minus mu and U V equal to 0. Okay? But this difference is non-zero. So this is implied as U V is 0 since lambda is not equal to mu. And we have done. Okay? So for self-adjoint linear operators, if we have two eigenvectors corresponding to distinct eigenvalues, then they are orthogonal to each other. Okay, so this is a salient features of self-adjoint linear operators. Another salient feature is that every eigenvalue of a self-adjoint linear operator should be real. Okay, so this is the case we have. All right. Now, an n times n complex matrix A is called Hermitian. Okay, if AH equal to A. So if the conjugate transpose of A is equal to A itself. Okay, and n times n complex our real matrix. And n times matrix is called symmetric. If A transpose is equal to A. Okay. Okay, now, so let T is a linear operator from with okay, so A is an n times n matrix over F. All right, so typically T is a linear operator on the Euclidean space. Now T is self-adjoint. Okay, now T is self-adjoint. If only if A is Hermitian. If A is Hermitian, when in the complex case and symmetric in the real case. Okay. Okay, now we have known that for this special kind of linear operator, the dagger, the T dagger, all right, it's AH X when F is equal to C and AT X when F equal to R. Right, so we already know that. Okay. Okay, so T is self-adjoint. If and only if T dagger is equal to T. So if and only if AH equal to A when F immediately equals C and AT is equal to A when F equal to R. And this is has been done. Okay, so for this reason, a complex Hermitian n times n matrix or a real a real symmetric n times n matrix is called self-adjoint. Okay, so we'll call matrix to be self-adjoint when it is Hermitian in the complex case, when it is real, is symmetric in the real case. Okay, these two kinds of matrices are called self-adjoint. Okay, so we use the same concept called self-adjoint. And so theorem 8.1.24 says that an n times n matrix, okay, A over F. Okay, so an arbitrary n times n matrix A over F is self-adjoint if and only if we have this functional relationship. Okay, so if and only if that. So to check whether a matrix is self-adjoint or not, you can check this functional relationship. This functional relationship must be true for all x and y in the n-dimensional Euclidean space. So okay, so we have a corollary 8.1.1 plus 2. All right, so let A is a self-adjoint n times n matrix over F. Then 1 every eigenvalue of A, if exists, must be real. Second, if U and V are eigenvectors of A corresponding to distinct eigenvalues lambda and mu respectively, then U must be orthogonal to V in the Euclidean space. And the proof is easy. This is the so just say, so this follows from, so A is self-adjoint. A is self-adjoint. If only if this T is self-adjoint. Okay, this T is self-adjoint. And if T is self-adjoint, then every eigenvalue is real. Okay, so this is follow from theorem 8.1.4 and theorem 8.1.2 plus 3. Okay, so that's easy. All right, and also similarly, we have a theorem, 8.1.f, that so T, a linear operator on a finite dimensional inner product space okay, so T is linear operator. All right, so T is self-adjoint if and only if its metric representation is self-adjoint. Where B is an also normal basis for V. Okay, so this is the same. So this is follow from theorem (8.1.e) and theorem 8.1.4. Okay. Okay, so right, so I stop here, and so now we have we are prepared to further discuss the spectral theorems, and we will talk about that next week. That would be the last week of this semester for the class lecture. Okay.